So today will be a very sketchy overview of capacity theory and related topics. Right? So, yeah, and exercises. I still didn't get around to finish the correction of your handouts, handies. This will happen next week sometime. I guess whoever was still handing in problem assignment will pass, probably. So that won't be a problem. So this will be, I'll do that together. I don't have the statistics for the whole period anyway. And so I'll do that together with David when he comes back. He'll be with us for another few weeks, or maybe a week, and then go on to work with the Bosch company. Start at zero, but anyway, you can't really. I wouldn't talk him out of that because an academic career is extremely risky. So if you find something good he wants to do, we shouldn't keep him, or even try to. Anyway, okay, so let us start.
One question,
yeah.
The exercise sheet due to tomorrow, should we hand it?
Yeah, just give it to Wiebke Möller, to my secretary.
Okay.
I'll be probably around, but I can't promise, or give it to somebody down there. Put it on David's desk or something like that. Okay. I have the others on my desk, but anyway, there won't be a problem handing that in. Okay, great. Okay, so let's start now. Today's lecture will be an extremely sketchy overview of theory of capacities and various entanglement quantities. And the characteristic property here is that we are looking at rates with which you can do certain tasks. In particular, working with noisy resources. Right? So my title for this is so we had a couple of conversions of resources I would not call noisy. Right? So we had some resource conversions noiseless or of pure resources. Let's say noiseless. So, for example, 1 qubit transmission plus 1 bit entanglement. So if you have a situation where somebody gives you copies of an entangled state, or gives two distant partners an entangled, one maximally entangled qubit, and you're able to send 1 qubit across a channel, then you convert that to 2 classical bits. Transmitted. And this was just called dense coding. And if you have 2 classical bits, then you can actually 1 qubit transmitted. This is called teleportation. So these are typical relations that tell you how certain types of resources can be traded for each other. Right? If you're able to do certain things, you can do something else. And there's a certain quantity of this resource used up in the process. Okay, so there's several others like that. And maybe we'll come to, when I've defined capacities, we'll see what capacities of certain noiseless resources are relative to each other. To distinguish what we do today from that is, so often have not So this requires a maximally entangled state. Now, if you think of practical ways of generating states, they might not turn out to be maximally entangled, but a bit noisy. Maybe it could be a mixed state. And so, if you have that, can you still do something interesting? And what can you do? And how often can you do it? And so on. So these are typical questions, or non-ideal transmission channel. So the qubit transmission that we have available here might be a general channel, not the identity. And here you're basically assuming that the channel that sends the qubit from Alice to Bob is an ideal channel. You just pass it on, and we didn't even discuss the noise. But in general, there would be noise on that process. So what do you get at the end? How well can you do things? Right? And so this is the real world. You have that all the time. So the question is, how can you, let me just mention a few So if the task is something like information transmission, and this could be classical or quantum information transmission, so this would be a task where you're given a noisy channel. This just means, noisy just means it's not an ideal channel. Right? It does something to the signal. Right? So it's a general CPT map, or general, what we define as a channel. Right? Use it to transmit classical or quantum information without errors. So this is one task. You would like to, you have a noisy channel and you try to use it to send error without errors, or essentially without errors. But we'll define that in detail. I had a list of those. I'd say, and so the quantity that measures this would be a capacity, or given a correlated state. Produce maximally entangled ones. classical communication. This is a long phrase. I think it's clear what it means. So we are in this separated lab scenario. We have Alice and Bob that live far apart from each other. They do have a telephone line between them, but they cannot directly send coherently quantum information. They don't have a quantum channel between them. But somebody gives them pairs of states that are somehow quantum correlated. Right? So for example, there could be a source in the middle that distributes somewhat entangled states, something fairly general, and now they're supposed to produce pure singlet, and they might want to do that because they want to run a teleportation process to actually send quantum information. Right? As soon as they have maximally entangled states, they can just run, and a classical channel, they're able to do quantum communication between them. Right? So this is the teleportation. But in order to get there, they have to improve on their noisy, that is not maximally entangled states. Right? So this is called entanglement distillation. There's a converse to this where they have maximally entangled state and they want to prepare copies of a certain other state, correlated state. And because the maximally entangled ones are kind of precious, they want to use as few of those as they can. So again, it's a question of relative simulation. So let's say, do some bullets here. Then other typical tasks would be given a source producing states with some probability. Send across an ideal channel of minimal size. So this is called data compression. And you're very familiar with that from packing files on your computer, right? So that would be the classical version. So the texts that you're producing have certain probability distribution of the symbols, or maybe also of pairs of symbols. And now you want to code that in bits of some sort, right? You want to devise a coding scheme so that everything is nicely digitized, but with the shortest average length, where the probability distribution comes from your distribution of the symbols. So you have German words have a typical distribution of single letters, pairs of letters, and so on. So there is a general probability distribution to plain text in a certain language. So you want to devise a compression scheme that codes this, packs this into just a bit string, and you try to minimize the length of that bit string. This is called data compression. And you can do the same thing in the quantum case, right? So you would have, instead of having letters, you would have quantum states. The bit string that you code on would be the qubits that you might send across an ideal channel, and that you could, in this scenario, you assume that you could store that well. And then the question is how many ideal qubits, or what is the size of the Hilbert space in which you can adequately represent this whatever came from the source. Right? And again, of course, there is a probability distribution in the background, so you want to do this with high probability. That's okay. So this is data compression. Then given either quantum channel or correlated states. Generate a perfectly correlated but private bit string. This is called key generation. So the aim here is that Alice and Bob, in the end of this process, would share a bit string. There would be a bit string that will be guaranteed to be the same, maybe with some bound on the errors, with the additional guarantee that whoever was intercepting or interacting with the messages that were sent back and forth will not be able to guess any of these bits. That means private. So, so whatever procedure has been applied to the messages that go back and forth over the quantum channel, right? Or maybe by manipulating these correlated states or something like that. So all this would be in the public domain, and but in the end you want to guarantee that the randomness that they share is actually separated or uncorrelated to anything that the eavesdropper might learn. And then you could use this for secure communication. Right? If you have a key like that, you just take an XOR of your key with a given message. That's called a one-time pad encryption. And that is guaranteed to be unbreakable, right? If this bit string is private. And so this is another typical task. What else do we have? For example, yes, so given a channel, a noisy channel, let's say. And entanglement for free. That is, the entanglement is for free. So send qubits without error. So this is entanglement assisted communication. So there's a whole basket full of tasks like that, and what they have in common is that there is an error criterion. You want to do it well, right? For example, for the compression, after you compress and send through a channel, you should be able to reconstruct the original signal with high fidelity or some low error measure. Or whenever I talk about just sending without error, it means that whatever you send into the channel comes out, and the overall channel has a CB norm distance to the identity which is close, small, or something like that. Right? So there is an error criteria, and these are tasks that you want to do many times. So actually, the interesting question is, a possible rate. So let me give you the pattern of a capacity definition. So a pattern for such definitions. So let's say given channels, let's say S and T, defined. So a quantity that, let me just call it epsilon, right, for error. And this is all, yeah, okay, so let me just write a definition. So the idea is that you would like to simulate that kind of definition by that channel. Right? So this is what you want to get, and this is what you have. Right? And so getting means you compare what you want with an encoded version of what you have. Right? So you're simulating an S-type channel by doing an encoding, then applying what you have, the channel that you have, then doing a decoding, where E and D are just arbitrary channels. Right? And you optimize that, and of course you make the error as small as possible. So this is the simulation error, or this is the error of simulating S by T. Okay, so now this typically happens between multiple copies of these channels. So let's say R is an achievable rate so this is the error of simulation, and this is the achievable rate for simulating S by T. So this is just a number, right? If now let us say that we get n uses of the channel, right? And we would like to get basically RS channels out of this. If a ratio of R of S channels to T channels, so this would be S tensor with R times N. So this is the lowest integer, no, the largest integer below Rn. R is just a real number. Right? So this says that roughly I get Rn uses Rn copies of S out of T copies of N copies of T. Right? So then this is and this is the error of that simulation, and we basically want to do this without errors. Right? So and the achievement here is not just doing anything, but doing it with vanishing errors. Now typically these errors will only be, you can only get them to vanish asymptotically, so that this goes to 0 as n goes to infinity. There are various ways of saying that. I mean, you could, this bracket is maybe the shortest notation-wise, but you could also say there is a sequence that goes to infinity of numbers here and numbers there, and their ratio goes to R or something like that. And then you have to ensure that the sequence is dense enough. Actually, I have an old paper with a PhD student, Dennis Ketchman, that called Thema con variazioni, that looks at all the possible variants of the capacity definition, including, of course, the error measure here. That you can do basically there are many options you have there, but you could say that all the reasonable options give the same definition, or give equivalent definitions. Okay, so this is an achievable rate. So the next thing is the capacity. So the capacity of, well, we could say of T for simulating S, yeah? Is C of, or let's say, let me Q, let's say Q of S and T, which is the soup of all the numbers so that R is achievable. Also the largest achievable rate is called the capacity. Okay, so so this is not easy to compute. Actually, this is a complete nightmare to compute. If I give you some two general channels, then solving this problem means that you have to optimize over general channels. Well, okay, that depends on the dimension, right? But it grows very badly with the dimension. So I think, yeah, last time you showed that this is actually can be done with semi-definite programs. So this is quite efficient for reasonably small dimension. But then comes this thing, right? So you look at this, an exponentially growing dimension. Right? The tensor product channel lives in the product of the Hilbert spaces. So this is exponentially growing with n. And you're supposed to compute a limit. And that is almost impossible. Right? So you really need an idea of how to do that. So,
is it known that the capacity is finite for like large number of interesting?
yes. Yes. We'll see. We'll see. I'll have a few things to say about that. Sometimes it's zero. So, for example, for trying to simulate when S is a quantum channel, or let's say an ideal quantum channel, maybe, and this is a classical channel. So you cannot send quantum information on classical channels. So that capacity is zero. Right? And the only achievable rate here is zero. Okay, but often it's positive, and one can show it's positive. Let me make that remark. So it's hard to compute period. It's just hard to compute. There are two different sorts of channels for which that problem has been solved for, let's say, for the quantum capacity. Then, but I would add, so that's one remark. So if you want to prove anything at all about capacities, it won't do to, well, if you can write down the definition, you get a few simple things, but if you want to show any non-trivial estimate, you will have to have an idea of how to do the E and the D, right? How to do the encoding and the decoding. And that might put you in a position so that you could prove something about that. So, for example, you have to know So if I have a channel so that this is small for some value of n, can I actually improve that to give a positive capacity? So, okay, so suppose I look at a problem like this for not so large n maybe, and I can see that this error is small. So the question is, can I get rid of the remaining errors? And if they're small enough, you can, and there's general schemes for producing error-corrected codes that would kill the remaining errors with a small loss of capacity. Right? So there is some ratio between this number and that number. And if this epsilon is small enough, you can show that actually you're already close to the capacity. Well, that's the sort of result that you need in order to make this a reasonable definition. Right? So you can tell that you're close to the capacity when this error is already small. That's how it should be. Okay, so so this is some formula for the capacity is called the coding theorem. And then a question that many people have thought about is converse coding theorems. That is, so you could say that R is a converse rate if epsilon of S tensor Rn P tensor n goes to 1. I put this funny factor 1/2 in here so that the largest value of this norm difference is 1, which is at the same time has this operational interpretation of the largest probability difference that you can get when you replace this by that in any environment, in any experiment involving maybe other systems and arbitrary preparations and measurements. Right? So this is the operational quantity, and this means that you will be able. So if this epsilon is 1 or close to 1, that means that you can detect the simulation attempt with probability 1. There will be something that is done completely wrong. Right? So there will be one test, one input state, and an output measurement, for which the probabilities for this one are 1 and for that one are 0. That's what, or almost 1 or almost 0. Right? So if you look at the definition, it only says that if you go above the capacity with your coding rate, then the errors will not go to 0. But they could, for example, oscillate or do something funny. Well, they can oscillate. That's another little lemma. But they could converge to something that is maybe just very small. Right? So if you're willing to accept small errors, very small errors maybe, then you might be actually able to code above the capacity rate. That's, at least this definition allows that. Right? Now the question is, what is the behavior of the errors when you're close to the capacity? And the sharpest thing would be to say that the capacity is a converse rate. Right? That would be called a strong converse theorem. I should say strong converse rate. That's the, sorry, I meant to say that. Right? The strong converse. So if you read about strong converses of coding theorems, this is what is meant, that if you try to go above the rate, then the errors will actually go to 1. Right? Okay. So now I said it's hard to compute, and of course it's very hard to compute if you have just general channels. But typically, actually, one of the channels will be an ideal channel. Right? So So then the important special cases. So when the thing that you want to simulate is the identity, so this is supposed to be CL, or let's just say C. Yeah? So this is identity on a classical bit. So then what you're trying to simulate is a completely classical transition probability, and or to a classical channel that should be as close as possible to errorless, right? And in this case, we just call C of S T just C of T. So this is the classical capacitor Q. I think I call this a Q, right? Yes. So the case where what you want to simulate is classical ideal transmission. You call the classical capacity, and if S is the identity on a 2x2 systems, so that's identity on a qubit system, then you're simulating qubit transmissions. So so this is a quantum bit. And in this case, we just call this Q of T, right? So with that S, we call this Q of T. Okay, so one of the things you might wonder about here is what is the importance of qubits here? This is an accidental choice of some value of the dimension. Well, it's not quite accidental, it's the smallest possible choice, but still it's somewhat arbitrary. Right? What if I'm interested in sending three-dimensional systems? And so let me just erase that, and I'll tell you a little bit about that. So the story there is essentially this is a choice of units. So why not the identity on the so the identity from C3. And so if I want to simulate that, what would the qubits tell me? Well, actually, this will be all equivalent. And that's basically the reason why for that qubit choice. So, but one way to approach this, and I think this tells you something about capacity, is compute C, which between ideal channels. And that will tell us how this works. So let's just, let's say we have the identity n, and the identity n, let's say CQ, and we ask for the errors here. This is what we would like to compute. Now, there are 4 combinations here, so I don't want to do them all, but just pick out some essential ones. So this is the thing that we want to simulate, that is the simulator, right? So let me just write what comes out. One thing that comes out is you can do this without errors when the thing that you want to simulate is actually smaller than what you have to simulate it, right? So first, I want to address the case that n is less than m. So what you want to simulate is actually of lower dimension of what you want to get. Now, in that case, if it's classical information that you're after, well, you just prepare those states, n different states, and they can be ideally distinguished at the output. So so this is certainly true for the pair C and CQ, and it's also true for QQ. These are these two numbers. So if you have a quantum system of low dimension, you can encode it without errors into a system of larger dimension. I'm not going to do this explicitly, but it's clear that you take, for the states, you just take a subspace and you take the corresponding measurements. You just throw away the rest of the subspace, basically. Now, the error is large for whenever you try anything quantum on a classical channel. So even if the dimension, even if n is as small as possible, so you're not very demanding, you want to send a qubit on a classical channel of arbitrary dimension. This is the classical translation impossible machine. So you'll make a finite error, a universal lower bound. I think it's 1, I'm not quite sure of that, but maybe it's something else. But it's certainly a finite bound, even when n is only a qubit and m is infinite or so. Right? You still cannot encode classical information. So no way for that combination are the errors going to 0. And this underlines the statement that all the capacities for quantum information on classical channels are 0. Okay, so now another interesting case is, maybe I should have written that first. So when n becomes larger than m, we are entering the regime where we're trying to stress the system that we have, right? To put more information on it than it will naturally take. Right? So when n is larger than m, and again, here I don't have to discuss anything, but this is for the combinations that are actually viable. Right? Then there will be an error bound that depends on n and n, will be lower bound on the errors. Right? And just so I think the lower bound actually is 1 minus n. Right? 1 minus, m. Careful now. N is larger, so when n goes to infinity, the errors do go to 1. But so this is the basic error bound. let's check this error bound maybe. Do we have the time? Yeah, maybe. So let's get this bound. It's a simple computation. And we could so get this lower bound for CC. Or maybe CQ doesn't really matter. Right? Yeah, CQ is nice. So this means we will have to look at the norm of the identity of a classical system on n points, and we have to compare that with an ED product where here we have m quantum. Yeah? So let's say quantum with Hilbert space Cn. And n, we're now in a situation where n is larger than n, right? We want to get more classical information through than the dimension indicates. And we want to compute this norm. Okay, so here would be the CB norm. It's larger than the CB norm is anyhow. We want a lower bound, so we don't have to think about this at all. Actually, in this case, it's equal, but this is certainly larger than some probability distribution minus, well, ED star applied to T. Right? So this is in the Schrödinger picture, and we look at the trace norm. We can stick in a particular probability distribution that doesn't come out right. Yeah? So, and for P, take, so P, the probability for some outcome is just 1 over n. So we take a uniform distribution here. So in some sense, we're looking at the mean errors. Yeah? And then this norm here, take, so this norm, what is that? It's the sum over x, okay. Then we have 1 over n here, minus, now, yeah, we have to say what the encoding is. So E will map a quantum state. So E is related to just choosing quantum states for every classical input, and D will correspond to a measurement, right? So an observer, because that's classical to quantum. So then, if you start with a state X, you get out the result Y with this probability, right? And we're summing so this is the output, is the input. We're just summing over the possible values of y with the weight that is the input state. So this is the probability distribution that we have is 1 over n, and this is what we get as a probability for x when we feed in this equidistribution. So this is 1 over n. This is the probability, so this is a sum. I can omit the absolute sign, so 1 minus sum y trace fx for y. So this again, we have to get a lower bound on this whole expression, so an upper bound on this will be good. Now, a density operator has norm less than 1. I do this because I want to use the normalization condition for the observer. Right? So this is, so because norm rho y has infinity norm less than 1, I can bound this by just a trace of f. So this is 1 over n, sum over x, 1 minus trace of fx. So this is equal to, well, we have n terms. So this, the first term is 1. Right? So this is 1 minus. Now the sum over x we can do, this is an observable, so this is the identity operator. And the trace, remember, is a trace in m dimensions. So this will give n. And then, so that's the bound. It's basically optimal. So it's, okay, so we see that we do make serious mistakes when we want to overcode very much. A little bit of overcoding will leave this very small, still small. So if m is just a small fraction, or n is just a marginally larger than n, that will be okay, but otherwise there will be proper errors. Okay, so now think of, we are now using that the identity of n factors, whether classical or quantum, doesn't matter. And you take some tensor power of that. So think of this as the identity channel on an n-dimensional Hilbert space. R-fold tensor power means that we have R tensor copies of that Hilbert space, so the dimension will be n to the R. So this is just equal to, the same in the classical case, so this is n to the R. Right, so we can use the bounds that we get here in order to get also the simulation errors between tensor powers of these guys, right? And then basically you have to look at this error terms. 1 minus m over n becomes 1 minus, now m is what we have to simulate, right? So this is m to the power n, and n to the power n times rate. So this is what the errors are. So this would be a lower bound to the simulation error of n-dimensional n copies of that with identity n times. Right? This is exactly the sort of thing that appears in the achievable rate definition. So this is basically m over n. Well, m over n to the power r, and the whole thing to the power n, up to rounding errors. Right? So this means that so we need that m over n to the r is less than 1 for the errors to go to 0. But this just means that r is larger than r times log n, so this r is larger than log n over log n. And on the other hand, if you have this inequality, then you actually get error 0. So this is the behavior of this quantity, of this error quantity. So this is the critical statement here. So the simulation of ideal channels of size n by ideal channels of size n is log m over log n. And again, we have this for classical or quantum. This doesn't really matter. If well, I shouldn't write a bracket here. If not classical or quantum. In this case, also, you clearly have a strong converse. So if you try to code above the rate, then this number will be smaller than 1, and so the error will go to 1. So that's well, but okay, the capacities for ideal channels should be an easy exercise. That's the one class for which we can compute them. But now, use the two-step coding inequality. Yes, one important thing here is a phenomenon called reversibility. That is, the rate for simulating one channel by the other is the same as 1 over the rate for doing it conversely. Right? So they can actually simulate each other without loss of rates. And now there's the two-step coding inequality, which says that C of ST is larger than C of SR, C of RT. So C, I call this Q. Sorry, I've made some last-minute decisions on notation, so I have to. C for capacity is not bad, actually, so maybe we should say C. Okay, so why is that true? Well, you can go through the definitions and work that out. This is actually a nice exercise. But the basic idea is if you can simulate a certain rate of R's by T, and you can use those R's to simulate a certain rate of S's, then this is the overall rate that you can get. This is one way of getting the coding. But of course, there may be a better way to use directly T to simulate S. And therefore, you have this inequality. Now,
wait, about the reversibility thing.
Reversibility would mean exactly that you have an equality here, right? So that you don't. Or well, actually, the capacity of S to simulate S is 1.
Yeah, but I mean, we have that we can simulate quantum with classical, but we can simulate classical with quantum, but can use the other way?
Not the other way.
Yeah, but
that's an extreme case of irreversibility.
Yeah, but I mean, shouldn't the capacity be like 1 over? Shouldn't the achievable rate be 1 over?
Okay, so what I'm saying is that this can be really an inequality. For example, if R is a classical channel and S is equal to T is an ideal qubit channel, this is 0 and this is 1. Right, so this can happen, and it's important that it can happen, and it actually will normally happen. We saw that if we take twice the same channel here, and then we have 1, right? And we just have the reversibility really means that 1 is larger than Q of S T times Q of TS. Right? This is, and equality means reversibility. And that is clearly what we have. This is a quotient, right? Sorry, maybe, I mean the equality here, that's what reversibility is. So, but this means that Q, if I have an arbitrary channel, so this is the capacity for getting n-level systems, ideally across T, then this is larger than log, well then let me write it out, Q of ideal n, ideal 2, times the whatever capacity we have for T, And then we can estimate that again. So we have a chain of inequality with equality, inequalities with equality. So this we've seen is log 2 over log n. So actually we see that this whole thing is log 2 over log n in whatever base. Doesn't depend on the base. Times. So to summarize that we use the qubit as a reference system here is a choice of units, right? So qubit reference is a choice of units. Namely, we measure the capacity, quantum or classical capacity in bit. And that is what we do classically as well. Right? So information theorists always take dual logarithms, this is a one of the dual logarithm, or what's it called? The base 2 logarithm of n. Right? So this is what the log that information theorists do. So if they talk to statistical mechanics people, you have to tell them that, oh, you're taking Boltzmann constant to be equal to log 2. Also, is it 1 over log 2? Something like that. So, okay. Now, I wonder what else I should tell you. There's so much that is a bit hard to make a selection now.
This whole part, it doesn't involve exchange of like source of entangled.
No, so this is the capacity without using entanglement assistance. If you use entanglement assistance, then you have to describe better. So then ETD becomes replaced by something that involves the whole protocol of how you can use the entanglement and what kind of classical messages you can send. Right? So this is the simplest encoding process where Alice does some encoding, and she does something that Bob doesn't know, and Bob does something that Alice doesn't know, and we apply D. Right? They just know that this pair is good for the channel, but they apply their operations completely independently of each other. Now, if they have entanglement assistance and some classical communication to go by, then they would replace that by a sequence of operations where they actually make measurements and send some signals back and forth, they talk about their results and so on. You have to write this down. And that is kind of cumbersome. But it can be done, right? So you can describe how to use entanglement in the encoding process. Then the ETD would be replaced by something that is more complex. Something like that, describing the protocol of communication and possible operations, happens always in this. This is especially trivial in the communication capacities. Another completely analogous problem actually is to convert entanglement, to distill entanglement. Right? The same, I think the pattern is still there. Yes, so this is the pattern for definitions. So how would we adapt this to entanglement distillation? Well, the objects that we're talking about will be correlated states between Alice and Bob, between whatever Hilbert spaces. Right? The error of simulation becomes the quality with which I can make state S look like state, produce a simulation of state S by, now comes the encoding process. The E and the D will not look like this, but there will be a sequence of operations, LOCC, local operations, classical communication. This is a protocol that is very hard to describe. Right? So to exactly describe which states can be obtained from which other states by local operations and classical communication is a hard thing. It's a little bit easier when the communication is only one way. But it's still hard, right? Because there can be many rounds of communication and measuring and exchanging data and so on. Right? Okay, but anyway, that's what you would insert. So the ETD gets replaced by some state that you produce from the state, let's now call it T, by LOCC. Then the CB norm gets replaced by the trace norm, and the rest is completely the same. Would be an achievable rate for entanglement conversion, and there would be a capacity for the entanglement conversion, which is then called the distillation rate, or something like that. Right? So, and then typically the the references would be at maximally entangled states. That is sort of the gold standard. And there is actually this problem that I addressed here, which is really not the hardest problem in the game, but that the reference doesn't really matter. This has a corollary. I mean, you could think of any pure state as a possible reference. So in the same way that I computed the capacities, the simulation capacities between ideal channels, you have to compute the simulation rates between arbitrary pure states. And there is something similar to this theorem. So, so let's say analogous. Distillation. I.e. converting n copies of correlated state, whatever it is, to nr copies of S, of reference. Now, of course, the states could be mixed that you're looking at, and so if S is equal to a singlet, let's say the reference, let's call them S and T, not the usual letters to choose for states, but just to stress the analogy here. Right? So if S is actually the singlet state, a maximally entangled state of 2 qubits, then I get C is called the distillable entanglement. Or the entanglement of distillation. And if you do it the other way around, you're sort of looking at the inverse problem of how to produce a state using nicely maximally correlated states, then you get something called the entanglement of formation. It's related to the entanglement of formation. It doesn't really matter what these things are called, right? But you get this problem of the reference. And so get rid of the reference. As above, by showing I still call this quantity C now, right? So C of so I take 2 pure states. So there is a simple formula for that, which is the entropy of trace over bar of psi. Now I have to. Well, I got it wrong. The wrong way around. Yeah. So this should be a phi. So it is a quotient of the entropies of the restrictions. So this is the trace of a bar. this is actually not quite so easy to show, right? So you have to work to see that the relevant rate, conversion rate between pure states is completely governed by the entropies of a restriction, or if you wish, by the Schmidt coefficients, the entropy of the Schmidt coefficient squared of these states. And there's also reversibility, as you can see from this formula. So it doesn't really matter which pure state you're trying to distill, you always get the same quantity of distillable entanglement. And you also get the same quantity of entanglement of formation by changing the reference, right? I didn't say what S is, right? So S of density operator rho is defined as the trace of a certain function of rho that we call eta, and eta of a positive number is minus t log t in your favorite base for positive t, and you continue it by 0, which is actually the limit as t goes to 0 of this function, right? So you make it continuous on the positive axis. So this function is applied in the functional calculus, which means that if you compute the trace of it, you might as well apply this function to each of the eigenvalues and sum the whole lot. So this is called the von Neumann entropy, introduced by von Neumann in 1927. And well, that's the famous story that Claude Shannon, when this kind of quantity came up in his information theory in the 40s, he asked von Neumann what he should call this quantity. And von Neumann told him, well, physicists call that the entropy. So this is why entropy is all over information theory. The word entropy comes from physics via von Neumann to Shannon. Anyway, this is here the entropy appears as something like log dimension for an ideal channel. And well, okay. It shows that the distillable, these conversion rates can be used for ideal resources, can be, any ideal resource, that is any pure state, can be used as a reference. And the quantities that come out are completely equivalent. Right? So I didn't continue there, but you get the same thing on the other end. So they have to be. Okay, so I don't have much time. So I have 10 minutes, so I'll just tell you a few stories. I mean, like basic things that are known and are current lines of current research. So, of course, we wouldn't do all this if it were just for the ideal channels. Right? So this was just a warm-up round. Now, you want to do this for noisy channels, and the basic pattern that everybody tries to achieve in quantum information, or in the quantum information theory of information transmission, is an analog of Shannon's coding theorem. So in the classic case, we have Claude Shannon produced a simple formula for the capacity of a classical channel. Now, a classical channel is basically just a transition probability matrix. It tells you if your input is X, what is the probability to get Y at the output? Right? So this is a complete description of the channel for that purpose, right? On that level. Okay, so given these transition probabilities, the task is compute the capacity of the channel. And the definition of the capacity is exactly this, right? When I go classical everywhere, I get exactly the quantity that Claude Shannon computed in 48. And what you have to do in order to compute that is, well, this is how the entropies come in. A certain combination of entropies of the probabilities, of the transition probabilities. Actually, it's called the mutual information between the output and the input. probability distribution. They are correlated, of course, right? So we have two correlated random variables. And in that situation, there's a quantity called the mutual information. And this is basically just the difference between the total entropy and the sum of the two partial entropies. Okay, so this is a number, but it depends on the input, on the probability distribution of the inputs. So you maximize over that. But this is a maximization problem that is straightforward, right? This is about when I have maybe 7 different input signals. This is over probability distributions on 7 points. This is a low-dimensional optimization problem that is actually usually solved quite easily, right? So apart from solving this little maximization problem for the mutual information, this is an explicit formula. In particular, it's a formula that uses only one use of the channel. Okay, so this is what they call a single letter formula, because they call the different signals that you send the letters of the input system and output system, right? So these are the different options that can be sent, right? So in that sense, it's a single letter formula. You only look at one use of the channel. Now, the first capacity problem that was seriously looked at was classical information on quantum channel, in the quantum regime, right? So you make the channel quantum, but you're still trying to send classical information. Very practical problem because, well, you have maybe fiber optics transmission. Clearly you're sending qubits down the line, right? And you might improve your coding for classical purposes by doing this in a more clever way. Right? So this is why coding, why that sort of coding problem was interesting. Was seriously attacked first by Holliver in the 80s, I think. And he came up with an analog of the Shannon formula and showed that this is a lower bound to the capacity. So it's an achievable rate. And the way to achieve it was actually to use a tricky encoding and product measurements. This way around, I think, yeah. And it was, so the formula, so let's say chi was Holliver's capacity. Actually, when he gives a talk, he is a very modest man, and he would never talk about the Holliver capacity like everybody else does. He would say the chi capacity. Right? So I guess chi stands for Holliver. So the classical capacity is something like the limit over n uses of the channel of this chi capacity. Well, not something like it's exactly that. Right? So you can prove that this is a capacity formula. Now, this is great. So we do have a capacity formula. Computing the chi for a given t is the same sort of variational problem that Shannon had in his theorem. Only it has a really nasty feature that this has to be done for an asymptotically large channel, right? So with that exponentially exploding dimension. And doing this variational problem, so this is a nasty feature actually of many capacity formulas that we have. So there is a similar relationship for the quantum capacity. So it's also, this is an expression of entropies, in terms of entropies. And there's something called the coherent information that replaces the mutual information that would give you in a similar way, would give you the quantum capacity. So there is a formula for that, but evaluating this formula is a real killer because it involves an optimization of an asymptotically large problem. So everybody's looking for, maybe, hopefully, sometime, a single letter formula for this. The entanglement assisted capacity is another one of this in this game. Actually has a single letter formula derived by Peter Shaw, derived in the Shaw algorithm. So yes, so we do have capacity formulas, and it was for a long time an open problem to show that maybe this is even additive. Maybe it's actually true that pi of T1 tensor T2 is equal to the sum of these capacities. One inequality is trivial, right? Because if you have two channels that you can code on, you can just do the best you can for each kind of channel, and that gives you a subadditivity or superadditivity inequality. So one side is trivial, and the other was an open problem for a couple of years. Right? It was called the golden conjecture because it turned out to be also equivalent to the additivity of the entanglement formation and various other interesting quantities. So this kind of relation is called additivity. And so proving that would have given you a professorship anywhere where they're interested in quantum information, but it was killed by Matt Hastings, who didn't need a professorship. So, very clever. Although his writing is, well, if you want to understand the Hastings proof, it's good to go to secondary sources that have sort of written it out step by step. Let's put it that way. Right? So it took a while until actually this was completely accepted. But now it's very clear that this is in general false. So actually, this nice formula is next to useless. It gives you a sequence of improving lower bounds, but you don't really know how much you can gain. Okay, so this is the story of capacity formulas. Well, okay, there's a whole field of that one would call quantum Shannon theory, where that deals with this sort of asymptotic formula. Now, the current trend, however, is to go away from this asymptotic situation in two ways. One way is that we are always using n copies of the channel, T tensor n, right, in what I wrote. This means that successive uses of this channel are independent, but very often this is not the case. So actually there may be correlations between the channel. The overall transmission of n qubits might actually have memory effects between the different uses of the channel. So this is one direction in which one would certainly like to go. And the other direction is that, think for example of key distribution. Right? So this can also be phrased as an asymptotic problem. What is the rate of key that you can generate from a certain quantum state? Good problem, but practically useless. Because if you want to actually generate key, you're not in the asymptotic situation. And actually many of these theorems are of the kind that you can find a decoding that would do this, but this might not be a very practical thing to do. So in Shannon's theorem, for example, Shannon's original work, the key idea was random coding. That is, you basically choose your code randomly, and that is enough to achieve the capacity. But random codes means that you have huge code tables, actually exponentially large code tables in the block length, that would tell you how to do the coding, and the decoding is also a bomb. So actually in practical information technology, you don't use random coding, because this is extremely wasteful of memory resources. Right? So it's very good for the theoretical analysis, but to actually do it is a completely different thing. So in the same way, if you want to practically generate key, you actually have to give an explicit procedure of how to extract the key and how to throw away bits that, throwing away some of the bits will increase your security level, will also make the agreement between the keys better and so on. So there are various actually classical post-processing steps that you will have to do in order to really get a key. And in the end, you want to give your customer a guarantee that with probability less than epsilon, Eve might know a bit of yours. And well, roughly of that sort, but it depends explicitly on the error bound. Right? So the success criterion is something that is formulated not as errors will asymptotically go to zero, but as errors are small. That's the thing that you really want. Right? The capacity, the asymptotic theory is a good way to express that, and to prove something interesting about capacities, as I said, requires that you understand a lot about codes, and that might help you to show something for finite block lengths, or finite n, yeah? But you still have to do that. And this is the other direction that is gaining much strength in quantum information theory these days. So Shannon theory as an asymptotic theory is not the hottest thing in town at the moment, but rather looking at channels with memory and looking at a finite instance and getting explicit error bounds for various tasks like this. Okay, I guess I'll close there. Thank you for your attention, and see you later for getting your points and all that. Okay. Bye-bye.